All right, everybody, welcome. We are going to push forward in our content. We're going to start looking at interpreting the derivative and using it to kind of analyze functions and stuff like that. So we've been finding derivatives, essentially. We started off this semester with limits, and we quickly moved towards looking at derivatives, and we've been crunching through derivative rules. So right now, we have a whole bunch of rules for how to find derivatives, and we will continue to use those, which is good news for some of us, and maybe not so great news for others, but we'll get lots of practice on finding derivatives. But now, the goal of what we're doing is going to be taking those derivatives and seeing what kind of information we can get out of them. So we're going to start by talking about maxima and minima. We're going to talk about the differences between local maxes and local mins versus absolute maxes and absolute mins, and I expect that that's going to be a review. We've talked about those differences. We'll define those things just to make sure we're all on the same page, but we'll try and move towards the extreme value theorem. This is our second value theorem of the semester. We've done the intermediate value theorem, you might remember, and we have one more coming called the mean value theorem that we'll do, I think, in the next video. So we're going to hit this one. It's going to help us out with finding extreme values. And then we're going to define critical points. We'll make sure we get that definition locked in because that's going to be a really important term for us for the next while. And then at the very end, we'll just do a couple of examples of finding absolute maxes and mins using all the stuff that we've talked about. So let's talk about the differences between local maxes, local mins, and absolute maxes, absolute mins. Let's say I've got some sort of a function that I'm going to draw here. Let's say it looks something like this. It's got a whole bunch of different maximums and minimums on here, some of which are local maxes and local minimums. Some of them are absolute versions of those. So what I want you to do is to just maybe pause the video for a second, remind yourself with this picture what's going on, and then in a second we'll just talk about it. All right, so really quickly, we've got a bunch of local maxes and local mins. They look like right at these points here. So we've got a local max there, a local max there, and a local max over there. And then we've got two local minimums right there. Oh, that's a bad arrow. And right there. The absolute maximum is going to just be this one here. And you might remember that the difference is that this is just actually the biggest, tallest point. If we're talking about maximums and minimums, normally we'll try and think of height. And if you go ahead and follow this over to your y-axis, it's got the highest y value of all the y values on this picture. This is the lowest local min, but what you'll notice is that it's not the absolute minimum of our function. Why? Well, because our function goes down forever. So this is an interesting thing. We might not have absolute maxes or absolute mins. You could imagine if the other end of our function went up, then we might not have an absolute max or an absolute min. Things can be a little bit tricky. The local maximums and local minimums, we'll just kind of like circle them up here really quick. And this is kind of a weird thing. But we literally define these little circles that I've drawn as neighborhoods. That's the technical term that we give them once you get past calculus into more like analysis and topology and stuff like that. And essentially we just say like these are the tallest or the lowest y value points in these little neighborhoods in their little local area. And so that's why we call them local maxes and local mins. So here's our definitions. For an absolute max, we've got some function being defined on a set D. You can think of this as a domain containing some x value c. So that's actually in the domain. Our function is defined, meaning this is actually a y value here. If the y value at that point is bigger than or greater than or equal to all the other y values in the range, essentially, all the other outputs for all the inputs that are in the domain. This little symbol here means in. This says x is in D. You'll see that symbol a bunch. Excuse me. So if that's true, if this y value is greater than or equal to all the other y values in on our function, then we call f of c the absolute maximum value of f on that domain. And then we've got the exact same thing for less than or equal to. If it's less than or equal to all the other y values, then we call it an absolute minimum. The only difference for local maximums and local minimums is that now this interval is not necessarily the whole domain. And we'll also notice we've got this extra little tidbit here. We want our point to be in the domain, but not an ending point of the domain. And this is an interesting kind of little clarification that we're going to keep focusing on. We're going to keep thinking about points in the domain that are not ending points. Sometimes this is called an interior point. So when you see that in our text, they're really talking about some x value inside of an interval, but not on the ends, actually on the inside. So if you want, you could think of it as like only an open interval, although it could be a closed interval, and we just won't consider the ending points. Anyways, all that to say, if your y value is bigger than all the other y values in that interval, then cool, it's a local maximum. If your y value is less than all the other y values in that interval, then you've got a local minimum at that point. So that's all that we've got going on. Sometimes to get around this weird interior point idea, we'll just have to say that your function is defined on the interval around this point, making sure that we think of like both sides. So we really do want like some interval and some point actually on the inside here where you've got stuff around it on both sides. So that's all. That's what we're talking about here. The main thing is we want to figure out how to find these. We've been able to find interesting points in algebra classes. You've been able to find x-intercepts, y-intercepts, intersection points between functions, things like that. But finding these local maxes and local mins has never been something that you could actually do by hand. In general, you could do it for some specific functions, like for parabolas, it's just the vertex, and you guys have found vertices before. But what we're going to do is use some calculus to locate these points. So the big thing is the extreme value theorem here. This is a nice theorem that we're going to use a lot, and it just guarantees the existence of something. So we're going to say if f is a continuous function on a closed interval, then it must have both an absolute maximum and an absolute minimum on that interval. So two requirements: continuity, closed interval, and then we end up getting for free both an absolute max and an absolute min. Notice we don't know where they are. We just know that they show up. We know that this function that we're considering, as long as it's continuous on a closed interval, has to have an absolute maximum and an absolute minimum. So it's not like this picture that we drew where it doesn't have an absolute minimum, which makes sense. This is not on a closed interval, right? It goes down forever because of this end behavior. So you can kind of draw a whole bunch of pictures, and I would encourage you to do it. Draw some pictures that are continuous on closed intervals, and you'll be able to see what's going on here. Something like this. You can say, oh, okay, this ending point here is the absolute max. This other ending point on the left is the absolute minimum. That's what's going on. If you had something with a discontinuity, you could see why that could be a problem. Maybe like a vertical asymptote, right? Oh no, a vertical asymptote defeats this whole purpose because we have these unbounded y values. And so, of course, there's not an absolute max or an absolute min. There's all these other versions of what's going on here. Hopefully you can draw a couple to convince yourself what's happening. But the extreme value theorem is going to guarantee the existence of absolute extrema, both the minimum and the maximum, as long as your function was continuous on a closed interval. So that's cool. This will help us locate these, kind of. It just tells us that they're there. You'll notice it doesn't tell us where these things are. So we're going to need a little bit more than just that. So what we want to do is define this idea of a critical point. A critical point here, sometimes we'll just call it C. We'll just refer to the x value. This is a coordinate pair, x, y. But this point is called a critical point if a couple things are true. First, the derivative is either equal to 0 or doesn't exist, and that x value, C, is actually inside the domain of f. And again, not an ending point. So sometimes you'll see this. It's interior, or it's an interior point of the domain. it's not something right on the edge. So what that means is, like, for the square root function, for instance, we won't call this ending point a critical point because it's right on the very, very edge of the domain, because our domain is the closed interval from 0 to infinity. So that's the main distinction here. This is not always a distinction that's made in introductory calculus, but it's one that we're going to make. So we're going to think about this main criteria here, the derivative equaling 0 or the derivative not existing. We hopefully know a little bit about what that looks like visually, what that really means for us visually. Hopefully we remember that the derivative equaling 0 is really like a horizontal tangent line. So it could be something like that. And hopefully we remember that the derivative not existing is like a sharp corner or something like that. Or maybe it's like a vertical tangent line. So these ones are always harder to draw nicely. Like a vertical tangent line, right, like that. So we've got these kinds of options that we'll have to look at and find. So those are critical points. That's just the definition. So we'll be spending a bunch of time finding these points. So we'll be looking for where the derivative is equal to 0 or where it doesn't exist. You can imagine how that's going to go. We're going to find the derivative function, and then we'll set it equal to 0 or investigate where does it fail to exist. But once we find those points, we'll call those things critical points. And why are they really helpful? Well, what we're going to find out is that the local extreme value theorem says that every local max or local min has to have occurred at a critical point. The opposite ordering of this is not true. So it's not true that every critical point is a local max or local min. But every local maximum or local minimum is at a critical point. So if you just drew a local maximum like that, notice, hey, look, you've got that horizontal tangent line. Or maybe you had a sharp corner that looked like this. And if you flip both of these upside down, it doesn't really change anything other than the fact that we've got local minimums now, but we still have that horizontal tangent line or sharp corner where the derivative doesn't exist. Notice, though, again, there are other spots where the derivative might not exist or equal 0. So here's one where you've got a horizontal tangent line, but that's clearly not a local max or local min. And the picture that I drew earlier with the vertical tangent line, not a local max or local min, but we'd still call those things critical points. So critical points are going to help us find local maximums and local minimums. If we go back to the extreme value theorem, we said this guaranteed the existence of the absolute maxes and absolute mins, but we didn't know where. So this is called a lemma. A lemma is like a theorem, but it's like smaller. Normally it's like a result that comes from a theorem. So this is the extreme value theorem lemma. I normally just group these things together. If, and this is true for any function with absolute maxes and absolute mins, any absolute max or absolute min has to occur at either a critical point of f or an ending point of a closed interval. So there's only those two options. So local maximums and local minimums have to occur at critical points. Absolute maximums and absolute minimums can occur at the ending points as well of a closed interval. Remember, when we defined local maxes and local mins, we had that weird thing that said, like, okay, we got a point in the interval but not on the ends, right? Not an ending point. So that's the main distinction here. Absolute maxes and absolute mins can show up at the ending points of closed intervals as well as those critical points. So it might not seem like it, but this is as much information as we need to be able to go ahead and hunt some of these interesting features down. For instance, we can go ahead and find any critical points for this function. We've got some function. Critical points are spots where the derivative is equal 0 or the derivative doesn't exist. And then we'll have to check with the domain. Ooh, it's getting hard to write on this thing. So those are some things that we'll have to just try and keep in mind. So obviously, our first starting bit is going to be finding the derivative. So if f of x, I'm just going to rewrite this here, is x squared, natural log of x, you can imagine how we're going to find the derivative of this thing. Oh, man. It's a product rule. So we're still going to have to be up to snuff with all this kind of stuff. The derivative of x squared then is just 2x. The derivative of the natural log of x is 1 over x. And then we'll do uv prime plus uv prime. Wait, I think I said that wrong. uv prime plus u prime v. There we go. So we've got x squared times 1 over x. That's just, I'll write it out. So this is our derivative function. So we've got an x squared over x plus 2x natural log of x. I'll probably just call this x plus 2x natural log of x. But now I'm going to factor this. I've been talking about how this is going to be helpful later on, and now is the later on. So here's our derivative. The reason I want to factor this is because the whole point of it is I want to see if I can set this equal to 0, right? So I can. If I say f prime of x equals 0, that's really saying x times 1 plus 2 natural log of x equals 0. And it's nice to have this factored because this means either x equals 0 or this whole factor, 1 plus 2 natural log of x equals 0, which means, oops, let me first solve for the natural log of x. The natural log of x is going to be negative half. I'm going to subtract 1 from both sides, divide by 2, and that means that x is e to the negative half. So I have these two x values that set my derivative equal to 0. I also might want to look for where my derivative doesn't exist. My derivative doesn't exist when the natural log of x doesn't exist. So we'll say x equals 0 or x is less than 0, because the natural log gets screwed up at 0 or negative inputs. So what you'll notice is that this value here is really not a spot that sets this derivative equal to 0. It really makes it not exist. One of these things is equal to the 0, but this whole term here doesn't actually exist. So 0 times something that doesn't exist doesn't exist. But then, before we get too far along, we'll have to notice that we really want to check with the domain. So this is a really important part of this. The main thing is that for these critical points, they have to actually be points on our function. So what is the domain of our function? Well, our function's domain is going to just be any positive x values. I can't put in 0 and I can't put in negative values. Now this is f, not f prime. I'm talking about where this function itself exists, not where the derivative exists. The domain of the function is open interval around 0 up to infinity. That's a bad infinity sign. Oh, that's not much better, but oh well. So we have this open interval from 0 to infinity, and so what that means is that this part and this part aren't going to work for us because sure, the derivative doesn't exist there, but it's because the function doesn't exist. And if we're looking for critical points, we want points that are actually in the function's domain, inside of it. Now this is a positive number, this e to the negative half. That's really 1 over the square root of e. Negative exponent is in the denominator. Half means square root. So this is our critical point. If you want, we could find the y value that goes with it. Y is equal to f of 1 over root e, or e to the negative half. But I'll let you mess around with that. It's going to be pretty ugly. You don't need to. Well, let's just do it really quick. I'm going to put in e to the negative half. It'll be a little easier. All right, so that means that this is e to the negative half squared times the natural log of e to the negative half. E to the negative half squared is going to be e to the negative 1. Natural log of e to the negative half is negative half. So this is negative 1 over 2e. All this to say, my critical point is 1 over root e, comma, negative 1 over 2e. A lot of times we'll just define the critical point by the x value itself and not the y value. if I want the y value, I'll ask for it. Some places will make a distinction between critical numbers and critical points, where the critical number is the x value and the critical point is the actual set of coordinates. I'm not going to make that big distinction. I'll probably just use them interchangeably. And if I want y values, I'll ask you specifically for them. So if I just ask you for finding critical points like this, you can just give me the x value. But I want you to remember this is actually a point on this curve. And it's a point on this curve where the derivative specifically is equal to 0. So we've got a horizontal tangent line showing up there. Cool. So that's all we're asking for in this example. In this next one, we've got this other function, and we've got an interval. We want to find any absolute extrema. Well, first off, we can notice that this function is a continuous function. It's a product of two functions that are continuous on any open interval. From negative infinity to infinity is going to be fine. All real numbers, it's continuous. But anyways, it's continuous then on this closed interval. Since it's continuous on the closed interval, the extreme value theorem is going to kick in. That was that value theorem that we learned about. The extreme value theorem says that there are going to guaranteed be both absolute maxes and absolute mins on this interval. And if you remember, we had that little lemma that says not only are we guaranteeing that they're both here, but we know exactly where they're going to show up. They're going to show up at critical points or ending points. Now, ending points, I already know what the ending points are. I'm given this interval. I know the ending points are at x equals -2 and at x equals 4. I can find the critical points by just doing the exact same thing that we did up here for this problem. We're going to take the derivative of this, look at where it's equal to 0, look at where it doesn't exist, make sure that that's in the domain. In this case, our domain is -2 to 4 because that's the interval we care about. And then once we have those critical points and ending points, we just have to figure out which one is the absolute maximum and which one is the absolute minimum. And it's really easy to do that because all we care about there is which one has the very biggest y value and which one has the smallest. And if we have a list of all the possible options, then we just have to compare y values. So that won't be too hard. So let's go ahead and do this. I'm going to give you a minute. Go ahead and find the derivative of this thing. Brush up on that. Notice you're going to have to use like a product and a chain rule on this. So take a second to do that. Find your critical points, and then you can unpause this video and we'll pick it up from there. So go ahead and pause that. All right, so it took a little bit maybe to find the derivative. I want to walk you through one little thing that I'm doing just to maybe help. You might have things looking like this right off the bat. That's just from doing the product rule. Notice I had to do a little tiny chain rule to find v prime. I brought my 2 out front, and then I had to multiply by that -1 because that's the derivative of my inside part. So keep an eye on that. That's really a -2 because we're multiplying by this negative coefficient. Anyways, what I've done is I've forced this to be a fraction. This second term, I wanted it to be a fraction over x to the 1/3 so I could find common denominators. So I just called x to the 2/3 x to the 1 over x to the 1/3. It's the same thing. But once I've done that, then I can find common denominator, 3x to the 1/3, and go ahead and push these fractions together. The reason I want to do that is that if I'm looking for where my derivative is equal to 0 or non-existent, it's really hard sometimes to do that with multiple terms. It's going to be really easy to do that when we have one fraction, a numerator and a denominator. So anyways, see if you can follow the algebra through, but I've got this ugly fraction, 18 minus 30x plus 8x squared, which I can factor a little bit more. I'll pull this up here. Maybe I'll rewrite this. I'll call it 2 times 4x squared minus 15x plus 9 over 3x to the 1/3. So this is really my derivative. If I'm looking for critical points, then all I need to do is see where the numerator is equal to 0, because that'll mean my whole fraction is equal to 0, and that's the spot where my derivative is equal to 0. And I might want to take a look at where my denominator equals 0, because if I divide by 0, that means my derivative doesn't exist. So right off the bat, I can see a critical point. X equals 0 is going to be a critical point. If I put 0 in for x, I've got a cube root of 0 times 3. That's going to be a 0 in my denominator. Notice that is also in the domain of my function. It's between -2 and 4. My function is going to be fine. If I plug 0 into this thing, I'm going to get 0 times 3 squared, or 0 times 9, which is still 0, whatever. But that's my point. So here's one of my critical points. The other one is going to be where this stuff equals 0. And that might be a little bit trickier. I'll probably go to a blank page here because we'll have to factor this little polynomial here to set it equal to 0. So we might get 2 more critical points out of this thing. So let me see if I can just grab this. I don't know if this works nicely. It's not too bad. It's a little messy. So let me erase some of that stuff there. And it looks like, did I forget an end parenthesis? No, I just didn't grab it. Okay. There we go. So now I'll go ahead and factor this thing. I'm looking for numbers that are going to multiply together to get 36 and add to get -15. Oh, this is going to be a mess. That's going to be 12 and 3, right? -12 and -3? Yeah, okay. So 2 times 4x squared minus 3x minus 12x plus 9. You can factor this however you do it. This is how I do things. I know there's probably some better tricks on how that'll work, but I don't know what they are. This one I can pull out a factor of x, and I'm left with 4x minus 3. And then I can see I'm going to pull out a factor of -3, and I'm left with 4x minus 3. And then I can factor out this 4x minus 3, and this is what I'm left with in the numerator. Okay, all that to say, it's pretty easy to find my critical points now. My critical points are 3. That's where this factor is going to be 0. Then I've got a 3/4. That's where this factor is going to be equal to 0. And then I've got 0. That's where this denominator is equal to 0. So these are 2 spots where g prime is equal to 0. And this is one where g prime does not exist. What we care about, though, is finding absolute maxes and absolute mins, which is not going to be that hard because what we have now is a whole list of possibilities. We have a bunch of x values, and we want to compare their corresponding y values. We've got 0, 3/4, 3, 3/4, and 0, and we're looking at this interval here, -2 to 4. So we've got -2, 0, 3/4, 3, and 4. We have our 2 ending points, and we have our 3 critical numbers. And all we need to do is compare the y values here. So I'll let you go ahead, grab your function right here. Let me rewrite this out. G of x is x to the 2/3 times 3 minus x squared. And you're just going to start plugging these values in for x and see what kind of outputs you're going to get here. And all you need to do is compare them. So again, pause the video, run through that really briefly, see if you can find all 5 of these y values, and that should work out pretty well. Hopefully you're getting something like this. So at the x value of -2, we get the y value of 25 times the cube root of 4. That's our biggest y value that we get out of any of these things. So that is the absolute max of our function. Our absolute maximum shows up at the ending point, -2. But specifically, we care about the y value. Our absolute minimum shows up at 2 different spots. It's the same thing, though. In both cases, our absolute minimum is 0. But it shows up at both of these critical numbers, 0 and 3. If you put 0 into this function, you get 0. If you put 3 into this function, you also get 0. So our absolute maximum, we'd say, is 25 times the cube root of 4, and our absolute minimum, we'd say, is 0. Remember, I'm going to go all the way back to our definition here. When we're talking about our definition, we were looking at just the y value. We said our y value is the absolute maximum or the absolute minimum. So we really don't care a lot about the x value. So that's why when I'm talking about these, I'm referring to specifically these numbers. Anyways, that's how that goes. This is a relatively complicated example, mostly because I set this function up to be a little bit tricky to find the derivative, a little bit tricky to factor. So things should be a little bit easier than this for some of our other examples. Cool. That's what we've got on this. Good luck. Start jumping into that.